Hello there, AB students. I hope you're doing well. If all is going well, this is Friday. Mrs. Smith is your sub, and we're going to do a warm-up on tonight's homework 21-22. So you'll need that out. Then we'll do some notes on 21-22. Then we'll go over the homework from yesterday. So here we go. I'm on a homework that looks like, sorry about that. This at the top, set 21-22 derivative practice and transformations of graphs. I want to go to the second row, third box. And as a warm-up, would you use the alternate definition of the derivative, which you learned yesterday, to find the derivative or the slope of the tangent to the graph at 0, given that the function is x squared plus 2x. Mrs. Smith, if you would pause the video while they work on that, should take them about 3-4 minutes if they have a clue. Then play when it looks like they're ready. Okay, let's see how you did. Now, you didn't have to write the universal definition, but the universal or the general alternate definition is this. It's used to find the slope at a point. We talked yesterday about how if you take this in bits and pieces, it'll go better when you're new. So the first thing I'm going to do is identify what A is. A represents the point at which you're finding the slope. So if I put that in first, it's the limit as x approaches 0 of f of x minus f of 0 over x minus 0. That's the derivative at 0. That should probably be on the left side, but that's okay. Now I'm going to put in the function. The limit is delta as x, not delta x. X goes to 0. F of x is x squared plus 2x. F of 0 is 0 squared plus 0 over 0 over x minus 0. Or just x. Okay, now that's 0 over 0 because the idea is you're trying to find change between 2 points that are so close together that the change in y is approaching 0. The change in x is approaching 0. Every definition of the derivative is approaching 0 over 0, which is, there's an answer. It's indeterminate. We just need to do more. In this case, we can divide out an x and then evaluate the limit. If we put in 0 then, we get a answer of 2. The slope at 0, or the instantaneous rate of change at 0, is 2. Now, if you don't have to graph this, but if you think about this, this is a parabola with zeros at 0 and -2, opening up. And so the idea that the tangent slope here would be 2 seems to make sense, right? So hopefully that went well. And if not, we'll talk about it on Tuesday. Now, would you get out in front of you the notes for review of graph transformations? It should look something like this. I'll go through this fairly quickly. I will spend a little more time on the back because it's something you haven't seen before. And hopefully it will go well. In pre-calculus and in Algebra 3, and even in algebra, way back to Algebra 1, you learned how to take a parent graph or basic graph and change it around a little. There's a lot of different ways to do that. We're going to review that. But it's always important at all levels of math that you can check your work by making a table. If you're not sure, ask Matt. Make a table, Turkey. Now, you need to be able to do that on complicated functions. So let me give you a little practice here. Imagine that this is the graph of f of x for all these notes. You might label it. I wish I would have done that. Let's practice with the table here. Imagine if I gave you that g of x was a function that related to f through a lot of complicated additions or transformations, you would need to be able to track those transformations and check. So let's do one or two together. Say I wanted G at -4. I could plug in to G, and it's 2 minus f of absolute value of -4 plus 1. I could simplify inside. That's absolute value of -3, which is 3. Now at the point where you've isolated and cleaned up the inside, now you can go to the graph as a reference. F at 3 is -3. And so it's 2 minus -3. That should be 5. Okay? Now you do the next one as I do it with you. All right. So if I put -1 into G for x, I get f at 0. F at 0 is 3, and 2 minus 3 is -1. -1. Hopefully that went well. If not, check and talk with your math amigos. Hey, did Rickman screw up, or did you mess up? And figure it out. Now try the last one, G at 2. I'm getting 5 for that also. All right. Absolute value tends to do that, causes similarity between two sides. We'll talk about that in a minute. All right. Now, you've got a basic check your work kind of idea, but now let's talk about the graph. Using that same graph on the top with two quarter circles and a linear part to it, let's talk about what these would do. When you shift a graph, that's called translation. It depends on what sign and where you add, inside or outside. If you add one inside the x, well, then it changes x, and therefore it shifts it horizontally. Will adding one shift it right or left? I hope you said left. So if you take that base graph and look at those interesting points and shift them left, then keep in mind that a leftward shift will only change the x coordinates. So that'll change to -5. Darn it, -5, -1. -5, -1. -5, -1. 1, 2, 3, 4, 5, -1. That's the first point. That second point here, that was at -3, 0, will be x changed only to -4, 0. The whole graph gets shifted left. You get the idea. And the end point, instead of being at 3, 1, would go to 2, 1. So quarter circle, linear. I hope you said something like that. What if you add outside the function? Well, given that the function is y, then adding to the function changes y. In this case, it doesn't go the opposite of what you might think. It's logical. Up 1 shifts it vertically. Up 1. Now, in the interest of time, I assume you could shift that graph up 1. So let's bypass sketching that, and let's just go to the stretching and squishing kind of thing. What's the fancy word for this? Gosh, rotation, translation, reflection, dilation? I can't remember. Anyway, the idea is what happens when you multiply or divide inside or outside. So let's look at the 4 cases. Now, I have a hard time remembering this, but I'm really good with sinusoids. So I use sinusoids as a guide. If I said the sine of x, then the period would be 2 pi. But the sine of 2x would cause the period to be halved. And so it is multiplying inside is a horizontal compression. Now, because it's horizontal, I'm going to focus on what happens to the x at the interesting points. I'll leave the y. So this point here, -4, -1. If I compress the x, leave the y, then it would become -2, -1. -2, -1. This point here, horizontally squish the -3, it becomes -3 halves, 0. -3 halves, 0. Now, as far as the 0 up there, halving 0 has no change, and so it's a little more tight quarter circles. And then at the far right side, instead of 3, -3, I'm going to change the x by halving it, 3 halves, -3. It's an altogether horizontal compression. So by the same token, x over 2, like a sinusoid, would cause the wave to lengthen to 4 pi, dividing inside, or multiplying by something between 0 and 1, I suppose, is a horizontal stretch. Now I'm going to take the horizontal component, the x, and double it this time. So instead of -4, -1, I'll go to -8, -1, which might not even be on the graph. -1. That x-axis point that was at -3, 0, now will be at -6, 0. Again, 0 being changed by a factor doesn't change, it's still 0. So I've got these quarter circles being stretched. And then finally, that point that was 3, -3 at the far right, the x will double, it becomes 6, -3. All right, I prefer to be teaching this in class and asking for participation, but it's hard in this case. And those should meet, by the way, that should be continuous. All right. If you multiply it outside, then you're changing y. Just like sine of x normally has a amplitude of 1, 2 sine of x will have an amplitude of 2. It'll leave the x's, change the y's, so it's a horizontal, not horizontal, vertical stretch if it's more than 1. I'm going to look at each point, leave the x, change the y. So this leftmost point, leave the x, -4, change the y, now to -2. 3, 0, -3, 0. Multiplying the y by 2 doesn't change that because it's 0. But on the y-axis, instead of that maximum point being at 3, it'll be twice as much at 6. And likewise, 3, -3, the x stays the same, the y changes. And that's supposed to be linear. You get the idea. We'll skip the last one, but I hope you're going to say it's going to be a vertical compression. You divide the y's, divide each y by 2, leave the x alone. Okay. All right, let's go to reflection. Reflection, flip it over. All right, if you still are talking that base graph, if you change signs of the inside x, then you're changing x from positive to negative, and it'll cause reflection across the y-axis. So if you reflect across the y-axis, then those semicircles will be on the right. I gotta press it or bend it the right way. And the linear part will be on the left. terrible, but you get the idea. If you have a negative outside, that's changing the sign of y. If you change the sign of y from positive to negative, then it causes a reflection across the x-axis. So if you are able to visualize that, uh-oh, that's not cool. Didn't mean to do that. All right, so if you go across the y-axis, then instead of a min at 3, -3, you're going to have a max at 3, +3. It changes the sign of the y. Instead of a max at 0, 3, you'll have a min at 0, -3. The x-intercept stays the same, and the y. Then, can you get your mind around how to bend it? It bends like this. All right, cool. Hopefully all that was a review. And let's go to what is new. Absolute value. You might have touched on this, one of these two, but I don't think the other. So here goes, people. There's two very different situations depending on where you put the absolute value. We know absolute value doesn't affect positives, but does affect negatives. So if you keep that in mind, that's the conceptual part of it. No effect on positives, opposite for negatives. Just a second, there's an assembly or an announcement going on. Okay, so here goes. When you have absolute value on the x itself, the positive x's, the absolute value will do absolutely nothing, and so there'll be no change. So when you have absolute value inside, the right part of the graph stays the same because the absolute value didn't change the x. Positive x's, exactly the same. So this side here, no, would be exactly the same. Now, we know that when they're negative x's, they get, first of all, negated. Negative x's will be made like positives. And so the left side is a reflection of, or will be exactly like the right side. So now the left side will look like that. Now you might say, well, what happens to those semicircles? And the answer is, well, they never get to happen because those negative values never get thrown into the function. All right, so that's absolute value inside. The easier one is absolute value outside. This is changing the sign of y. When y's are positive, or f values are positive, there is no change. Now think about where are y's positive. Is that right, left, or top, bottom? And I hope you're saying that the top part of the graph, there is no change. Now if you look at the graph, the top part of the graph here, and I think it goes to -3. There's no change. Here goes the other part, though. Where y is negative, this is not going to cause a reflection. I know you think, well, okay, this will be a reflection too. That's not a reflection. Y's are negative. The function makes the y values, so it'll still make that little tiny circle and all that stuff. But what will happen to them is instead of becoming negative y's, they'll get made positive, and they'll be reflected up above the x-axis. So that part of the graph that was here, I have my circle bending, yes. the part of the graph that was here, I can't get a negative y out of that. There's no way to make that happen because of the absolute value. This part will be reflected up and it'll actually look like that. And this part of the graph that was here gets reflected up, and so it becomes positive. So those reflect above the x-axis. Now, let's see, using those notes as a guide, if you can do this. Try these three. You should, from the green book, know how to graph a cube. Keep in mind you've got an x cubed shape, and this gives you zeros if they're factored form. And a square is a bounce or a double root. Try that first graph. And if you're confident, go on to the next two. You might check with somebody around you to see if you have the same graph on one before you do 2 and 3. All right. So I hope you said that there's zeros at 0 and positive 1. And the graph will come down, go down to negative infinity on the left, go through 0, bounce 1, and head up. So that's what the graph should look like. I wish I would have made that root a little further away so I got better separation there, but next time I'll do that. All right, now, if you didn't have that, fix it. But if you do have that, then continue on and try 2 and 3. Pause the video, Ms. Smith and Mrs. Smith, and I'll go over it in a minute. All right, let's see how you did. Now, this is absolute value outside. So it should cause the positive y's, which were here, to be unchanged. Absolute value doesn't do anything to the positive y's. What it does change is the part of the graph that was below the axis. Now it should be reflected up. So hopefully you have something like that. All right. Now, the other one, when the absolute value is on the x, the positive x's, so the right side of the graph is unchanged. That's this. The left side of the graph is a reflection of the right side of the graph. So it should also have a bounce, but at -1, and go up like that. All right. Hopefully that's what you got. And if not, then make yourself a note and correct your notes, please. You never want your notes to be on. All right. Shift gears then. Now let's talk about the homework. Would you get out the homework that you're grading here? This is not something, not something, not something. All right, let's talk about a few problems off the homework, and then the rest of the time you'll be working together, fixing stuff, and working on tonight's homework. Here goes. One of the ones I want to talk about is 20.1. It said, express the distance from the, I'm going to draw over here. I know that's not this problem, but from y equals 2x plus 1 to the point 2, 3, express the distance in terms of x only. Now this is not a one-off. This is meant to prepare you for a calc ideal called optimization. I want to talk about the distance from here. There's lots of distances, certainly. And there is a point that's closest, and that's the calculus part of it, but we're not doing that part. I do know that the distance from 2, 3 to some point is yield distance formula / Pythagorean theorem reimagined here. And so that's where I'm at here. I hope you said it's the difference in the x's, difference in the y squared to make a right triangle, and square rooted. Now, that's a great start. If you got that far, that's good. Now we have to deal with this part in terms of x only. In terms of x only implies we can't have y. we have to put something in for y. What is y equivalent to in this problem? And so the next step is then to say, all right, I'm going to leave this part, it's fine, but in place of y goes 2x plus 1. In place of y, you put its equivalent, 2x plus 1, and boom. Now, if you did more, great, good for you, but I don't need any more. I've answered the question. I did the distance. It's in terms of x only. I'm good to go. I will look at those definitions of the derivative myself to see if you're doing things well. Go to 20, number 7. It says this is largely a graph it in your calculator kind of exercise. Now, I want to review this on 2 levels. First of all, if you wanted to graph this in your calculator the way it was, feel free to go grab a calculator if you want. I could switch to graph entry and turn it to a relation and type in x squared plus y, goodness, y squared equals, I think it was 9. And boom, you've got a graph. And then there's all these questions about, does it look like a circle? That's a remnant of the old calculator questions when it was a rectangular screen and it would stretch the circle. So ignore that. Don't worry about that. All right. Now, all that's great. But I want you to be able to graph in relation mode because it's a super feature of the calculator. But for calculus purposes, there are a lot of times when relation mode is no good. The calculator, in order to do some of the things that we want it to do, integrate, differentiate, we want it in function notation. So you need to be able to also put this in function notation. That means solve for y. It's got to pass the vertical line test, which you can see that a circle doesn't. The only way I'm going to take this equation and make it a function is if I move the x squared square root, but keep in mind then that now you're talking when you square root it's plus or minus. Now the top is the positive root. The bottom is the negative root. And so when you graph those two, it should make that same graph. So if I go back to function mode, graph entry type, change it back to function mode. If I do the root of 9 minus x squared, it's right on top and it barely shows. And if I then did, oops, the opposite root of 9 minus x squared, I am not doing it. The opposite of the root of 9 minus x squared. That's the bottom. You can see it makes the circle. All right, that's the point. But you need to be able to do both is what I want you to understand. All right, these aren't in the back of the book because I changed 20 number 10. So f is natural log, g is e to the x. Take care here. This can be a little tricky. So make corrections. Fog is f composed on g, which means put g into f. If I put g into f, then it's log of e to the x. The domain, mark the domain here. X can be all reals because I have a problem. Never mind. That's a bit of a problem here. If x, yeah, no, I'm good. Sorry. X can be all reals because plugging negatives into E is okay. They'll come out positive. Plugging in 0 into E is okay. It'll come out positive. And so all that is cool. The domain is all reals. Hopefully then you simplified it down to X. The part that is a little bit of a gotcha is GOF, G composed on F. If I put f into g, then that means in there, e to the natural log of x. Now, here's the thing you need to understand. Domain has to be satisfied all the way throughout, not just simplified. So please don't think, okay, it's x, so it's all reals again. This here will break the minute you put in a negative. And so x or zeros. And so in this case, actually x must be positive. The domain is x is only positive. These would roughly be the same graph. This would be all reals because they're inverses and you're right back to x. But this graph, if you looked at it in your calculator, if you graphed e to the natural log of x, it would only be this part and x would not be included. For a simpler version of this, consider what the graphs of these would look like. X, square root of x squared, and the square root of x then squared. Now, I know students are tempted to say, want to say they're all x. They're all exactly the same graph. And they're not. This graph is all reals. This graph, because the square comes first, it's all reals. But this graph, it's not all reals. You cannot square root a negative, even if you square it after. And so this is not a line, but array. And if you graph that in your calculator, you'll see that too. All right. So my point is the domain has to be satisfied all along the way. Even if you simplify it, it's the domain of the original function, not the changed function. All right. That'll come into play later. F of x equals x times x minus 2 times x plus 3. If you go to 2016, it's not hard, but I hope you're clear on the graphs here because we need to be good at these. There's no way we're going to do area under the curve if you can't graph the curve to begin with. So I hope that you found the zeros through factored form. The zeros are 0, -4, and 2. You put a cube shape to it. And then you said, okay, it's above the x-axis on. Remember, in interval notation, it's left to right or low to high value. And you use parentheses if you want to exclude the endpoints and a bracket if you want to include. So above the x-axis does not include at the x-axis. So that's one set. This set here, left is 2, right is positive infinity, if that's quote unquote an endpoint, which it isn't. And so that's what we're looking at. All right. And then the last problem I had notes on last year, having questions on, is 20.19. X cubed plus 2x squared plus 3x plus k. I can't even read that myself, and I wrote that. X equals -1 is a 0. What does k have to be in order for that to happen? All right. Now, I don't know about you, but I approach this in a synthetic division-y kind of way. If -1 is a 0, then when I divide by -1, I should see a 0 remainder. Remember, the coefficients go here, 1, 2, 3, k. And then the process of synthetic division is the first number comes down, and then we multiply and record it in the next column, and then we add. And then again, we multiply and record it in the next column and add. And we multiply and we record it in the next column and add. Now, k minus 2 needs to equal 0, so that implies k must be 2. All right, hopefully that's good. If you have other questions to work through, work them through together. Put your homework in the basket, and your homework is set 21-22. Have a great Labor Day weekend, and I will see you next week.